Welcome back. So the second problem we're going to be covering is going to be cutting rods. So the problem statement is as follows. We're given a rod of length n and prices pi for I equal 1 to n, where pi is the price of a rod of length I. So a rod of length 2 would have a price of p2. So the problem involves a maximization problem, and it says find the maximum total revenue you can make by cutting and selling the rod. This is assuming that no cost for cutting the rod. So what does that really mean? So we basically have different lengths of rods correspond to different prices. So for example, if I sell one rod, its price might be $1. If I sell a rod of length 2, then its price would be 5. If I sell a rod of length 3, its price would be 8, and so on. And then let's say I have a rod of length 9. How can I cut it and make the most money off it using this? So let's say I have a rod of length 9. I could probably just sell the rod and get, so from this table I can see that if I sell it without cutting it in one piece, I would get $24. But if I cut it into one piece and then eight pieces, I can sell the one piece for $1 and the 8 pieces for $20, and that's $21, but that's still less than 24 that I would get from just selling it. Again, so there are so many different ways of cutting the rod. I can also cut it in 2 and 7 to get 17 plus $5. I can even cut it into 3 parts. So let's say I can cut it to 2, 2, and 5. And then that will give me $20, 5 plus 5 plus 9. Or I can cut it to 5 and 4. You know, there are so many different possibilities of how you can break a rod into different smaller rods and then sell them, and you want to maximize the profit. And that's basically what the problem is asking for. You're given a rod of length n, and you're supposed to, and the prices for different rods of length 1, 2, 3, 4 up to n, and it's asking you what's the most money you can make from that rod. Okay, so let's start thinking of this problem and how we would solve it. Automatically, you should start seeing some overlapping between the different subproblems. So, for example, it's clear that I can cut it if I cut a rod into 2 pieces and I find the maximum of the left part and the maximum profit that is from the left part and the maximum profit from the right part, then that would maximize my overall money. So you should automatically start thinking about, okay, there's something recursive here. I can feel that there's a recursive solution here. So let's say that we have the initial rod, right? And we divide it into n pieces. We haven't cut it yet, but we just divide it into n pieces. So 1, 2, 3 up to n. Its length is n, and it's divided into n sections. Now, one possible way of cutting this rod is to cut, in the first cut, you would cut a piece of length 1, sell that piece, and then find the optimal solution for the length n minus 1. So find the optimal price for the piece with length n minus 1 that is left, because I took one, right? So there's only a piece of length n minus 1 left. So I sell a piece of length 1, and I find the optimal solution for the remaining part, and that is one possible way of cutting it. So that would give me a revenue of P1, which is price for one piece, plus the revenue, the optimal revenue that I get for the piece of length n minus 1. So P1 plus Rn minus 1. Another way I can cut this is to cut a piece of length 2, sell that piece, and then find the optimal division or the optimum money that I can make from the rod of length n minus 2. So that will give me a revenue of P2 where I sold P2 is when I sold the piece for the small piece of rod, the small rod worth that was two units, and the remaining n-2 gives me a revenue of Rn-2. So the optimum for a rod of length n-2. Now I can keep going on doing that the same thing, or I can cut it 3 and then find the optimum for n-3, 4 and then find the optimum for n-4, all the way down up to cut the first n-1, the piece n-1, sell it for p n-1, then I find the optimum division for the last piece, and then finally the last option is I sell the whole rod for Pn, and then that's it. So basically I can either sell it for P1 plus Rn-1, or P2 plus Rn-2, or P3 plus Rn-3, or until all the way down until Pn-1 plus R1 or Pn. So whatever one of these options that gives me the maximum money or the maximum revenue, I should choose it. So the best choice for us, so Rn, the optimum revenue for this piece of length n is actually P1 plus Rn-1, or is the maximum of the following: P1 plus Rn-1, P2 plus Rn-2, all the way to Pn-1 plus R1 and Pn. So I find the maximum of if I find the maximum of all of these, then that's the maximum money that I can get for my rod of length n. To recap, we found that the recursive solution is actually Rn is equal to the maximum of P1 plus Rn-1 all the way to Pn-1 plus R1 or Pn. So we're going to be defining Rn as the maximum revenue you can make from a rod of length n. Then Rn is equal to maximum of P1 plus Rn-1, or P2 plus Rn-2, or P3 plus Rn-3, all the way to Pn-1 plus R1 or Pn plus R0, where basically R0 is 0, right? If you have a rod of length 0, then you cannot make any money on it, so you can only sell it for $0. So let's see an example of the recursive code written in C++. So we're going to be including IOStream and vector in this example. In case you don't know what vector is, do a quick reading on it. It's basically a smarter version of a dynamic array that C++ handles it for you. It's not very different from an array. It has the same syntax. I think 5 minutes of reading on Google, you should be good to go. Yeah. So we're going to be including IOStream and vector using namespace standard. We will define the function as revenue, is returning an integer of the amount we can earn, and it's taken 2 arguments, n, which is how long the rod is, and vector of prices, the number or the prices, PIs, that we're getting. So the base case is if n is 0, then we should return 0. Then I want to find the maximum value of prices prices n-1 i-1 plus the revenue I prices. So at first I'm going to set up a variable called maximum value, max val, and I'll set it up to -1, a small value. It doesn't have to be -1. It can be 0. It can be negative. It's just make sure that it's a number less than or equal to 0, so that the maximum value is actually chosen during the process. So we loop for int I equals 0 to, so I goes from 0 to n-1. We take care here for the indices, because C++ starts counting from 0 to n-1. So whenever we're using a vector, we should take care about the indices here. So we're going to be looping from I equals 0 to n minus 1. And then we're going to, inside the loop, we're going to initialize a new variable, temporary variable that will store the value of prices n minus I minus 1. So that, for example, when I is 0, it's going to store prices n minus 0 minus 1, which is prices n minus 1, which is price n, plus revenue of 0 prices, and revenue 0 is 0, so it's going to store Pn. And then if temp is bigger than maximum value, then just switch the value, because we want to find the maximum value of all these elements. So when I is equal to 1, it's going to be prices n minus 2, which is basically Pn minus 1, plus revenue of 1. So we cut a piece of n minus 1, and we sell it for prices n minus 2. Take care about the indices here, because it starts counting from 0 and not. So it's a bit confusing, but just make sure you, if you write it down on a piece of paper, you'll see that there's the indices problem changes a lot of things. So just make sure about the minus 1 and plus 1. It's not conceptually, basically the algorithm is finding the maximum of P0, P1, P0 plus Rn, or P1 plus Rn minus 1, and so on. But it's for C++ sake, for C++ syntax's sake, we're taking care of the indices here. So it's just minus 1. So yeah, this loop basically finds the maximum value in all the elements that we previously mentioned, and then finally it returns max value. And here I ran a small demo on prices of, so let's say an object of length 1 can be sold for $1, an object of length 2 can be sold for $5, an object of length 3 can be sold for 8, 4 can be sold for 9, and 5 can be sold for 10. And then I said, what is the optimum revenue if I want to sell a rod of length 5? And it turns out the answer was 13, because you can sell it for, you can break the rod into 2 pieces, 2 and 3, and sell the 2 for 5 and 3 for 8, and that gives you a profit of 13, which is more than any other combination that you would have chosen. So whatever the combination you would have chosen, 13 is the most you can make out of this n, out of a rod of length 5 with these prices. So is this, theoretically, this recursive solution should work for any input, but when we start, what happens when we start going to large input? And unfortunately, the last solution ends up being an exponential solution. To see why this happens, let's look at the recursion tree that happens. So I'll call CR here as the cut rod. It basically represents the function that we're calling. So let's say we're calling cut rod 4. Cut rod 4 here calls cut rod 3, cut rod 2, cut rod 1, and cut rod 0. But then 3 calls cut rod 2, cut rod 1, and then you can immediately see here that there are so many trees that will be repeated. For example, cut rod 2 here is repeated twice. Cut rod 1 is also repeated 3 times actually here. And you can basically see that so many of these subtrees are being called over and over and over again, and you should immediately start thinking, okay, why am I calling them? This is basically what leads to a very bad exponential solution. This takes 2 of n. We won't go into too much details about how to derive the actual exponential limit, but turns out this performs O of 2 to the n because of how many how many calls are being repetitively called, which have already been solved before. So you should immediately start thinking, okay, how do I reduce this dynamic? So what is the dynamic programming solution here? So we first let R0 to n be an empty array, and we initialize R0 as 0 because, again, the base case is if we have a rod of length 0, then we can only make $0 on it. We can't sell it for anything. So we start looping for I equal 1 to n. We set max val equal -1, like in the recursive solution. Then we go for j equal 1 to I, temp equal to prices j plus ri minus j, and then if temp is bigger than max val, then max val equal temp. And finally, after the inner loop, we do ri equal maximum value, and once both the loops have finished, we return Rn. So what is basically happening here is we are basically going for I equal 1, so we're first calculating R1, then R2, then R3, then R4, and then for each of them, let's say I'm calculating R4, so right now I'm calculating R4, bear with me. So let's say we're calculating R4, we go for j equal 1 to I, then I calculate price, so P of 1 plus R of I minus 1, which is 4 minus 1, which is R of 3. So I calculate P of 1 plus R of 3, then P of 2 plus R of 2, then P of 3 plus R of 1. And then you find the maximum of all of these three, and finally P of 4 plus R of 0. And then you find the maximum of all of these four values, and that's the value of Ri here, where we set it to maximum value of all these maximums, and that's basically the recurrence. And then I go to the next one. Once I'm done with R4, I start looking for R5. Once I'm done with R5, I go all the way up to until n. Once I've calculated n, I return Rn at the very end. So finally, let's look at the C++ code of what we just written in the past. So we're writing a new again, we're including IOStream vector and using namespace standard. We're writing a new function int_dp, which takes int n as an argument and a vector of the prices. We then make a new vector, which is r of size n plus 1. We set r0 equals 0, and then for I equal 1 to n, we set up int max val equal -1. Then again we do the same loop that we showed in the previous slide. Make sure you're doing prices j minus 1, because remember that C++ uses from 0 to n minus 1 indices. So we should be very careful about the indices here, or you might get some unexpected results. And finally, plus Ri minus j, and we set up Ri equal the maximum value, and we return Rn. So I tried running this code on DP5 prices, and again, using the same prices that we ran it before, and again it returned 5, which is exactly the same. So hopefully through this video you've seen how dynamic programming really takes a solution from, previously it was exponential, but now here we can see it's only 2 loops, and therefore it's O(n) squared solution. So it's O(n) squared solution, which is much better than a 2 to the power of n solution. So hopefully you can appreciate how dynamic programming takes the running time down a lot by dividing the recurrences and storing their values in. In the next video, we're going to be covering more dynamic programming problems, so stay tuned for that.